Welcome to our quantum deep dive.
Great to be here.
Today we're diving into something really foundational for where quantum tech is heading.
Yeah.
Quantum multiplexing.
Yeah, it's absolutely key. We'll be looking closely at it, drawing a lot from Yurgav Schneppet's essay on the topic.
Right, so quantum multiplexing, what is it really at its core?
Well, basically, it's about getting more out of your quantum channels. Instead of sending quantum information bit by bit, or rather qubit by qubit, you're sending multiple quantum states, multiple streams of information, all at the same time through the same pathway.
So like a quantum highway with multiple lanes instead of just one.
That's a decent analogy, yeah. It's a huge efficiency gain compared to classical methods, and it really hinges on leveraging quantum mechanics itself, the qubits.
Okay, so this efficiency boost, it's not just like clever engineering, it's fundamental physics, superposition and entanglement.
Exactly, that's the heart of it.
Yeah.
Classical bit is just 0 or 1, simple. But a qubit, well, a qubit can be in a superposition.
Meaning it's kind of both 0 and 1 at the same time, until you look.
Precisely. It exists as a probability wave, a mix described by that equation, alpha 0 wrangle plus beta 1 wrangle. That ability to hold multiple possibilities at once is what gives it more capacity.
Which is totally different from classical multiplexing, where you're just chopping up time slots or frequency bands.
Right. We're manipulating the quantum state itself. And that superposition allows for, exploring many computational paths in parallel in a quantum computer. Huge potential speed up.
And Schneppet's essay really drives home that this isn't just theory. It's critical for building things like a secure quantum internet, better quantum crypto,
and unlocking what quantum computers can really do. So our mission here is to really unpack how it works, why it matters, and where it's going based on Schneppet's analysis.
Okay. And Schneppet lays out some key questions his essay tackles, right?
Yes. Things like, what are the physical principles?
Yeah.
The math behind it? How does it differ from classical? What are the tech challenges? And of course, the applications, communication, computing, sensing.
So to really get it, Schneppet says we need to start with the quantum basics. Superposition, which we touched on, and entanglement.
Right, superposition first. That single alpha 0 wrangle plus beta 1 wrangled all a thing. Alpha 2 and beta 2 are the probabilities you'll measure 0 or 1. It's probabilistic, not definite, until measurement.
That both at once idea, crucial for parallel processing.
Exactly. And then entanglement. This is where it gets, well, even weirder, some might say.
The spooky action at a distance Einstein talked about.
That's the one. You link 2 or more qubits, they share a single quantum state, like same wrangle, 0, 1 wrangle, plus 1 wrangle, Schneppet's example. Measure 1, and you instantly know the state of the other, no matter how far apart they are.
Instantly. That's mind-bending.
It is, but incredibly useful for coordinating signals in multiplexing, and obviously for quantum cryptography. It creates these correlations without any classical signal needed between them.
Okay, so these states, superpositions, entangled pairs, that they sound complex. How do we describe them mathematically? Schneppet mentions Hilbert space.
Yeah, think of Hilbert space as the mathematical playground where quantum states live. Each possible state is a vector, a point in this multidimensional space. And operators are like tools we use to act on these states.
Tools like the Poly-X and Hadamard operators from the essay, what do they do?
So the Poly-X operator, X, it's simple. It just flips the qubit state. If it's 0, X makes it 1R, and vice versa, like a NOT gate.
Okay.
The Hadamard operator, H, is really important. It takes a definite state, like 0A, and puts it into that perfect 50-50 superposition of 0A and 1A. That's how we create the quantumness to begin with, often.
Got it. They're like the basic moves you can make on a qubit.
Pretty much. And the Schrödinger equation, well, that's the master equation that tells us how any quantum state changes over time.
So this quantum world operates very differently from our everyday classical world. Schneppet points out some key differences and the challenges that arise.
Yeah, a big one is probability versus certainty. Classical physics gives definite predictions. Quantum mechanics gives probabilities of outcomes. It's fundamentally statistical.
And non-locality, that entanglement thing again.
Exactly. That instantaneous connection defies classical intuition. There's nothing like it.
Then there's the measurement problem Schneppet mentions. Just looking changes things.
Right. When you measure a qubit in superposition, the superposition collapses. It instantly picks one state, 0 or 1, based on those probabilities, and the quantum fuzziness is gone. The active measurement isn't passive, it forces a choice.
And these systems are delicate? Decoherence?
Hugely delicate. Decoherence is maybe the biggest villain in quantum tech. Any little interaction with the outside world, a stray vibration, a bit of heat, can destroy the superposition or entanglement. Maintaining that quantum state is incredibly hard.
Okay, these quantum quirks really set the stage. So let's circle back to the main topic, quantum multiplexing itself. How does Schneeppot define it, given all this?
He defines it as transmitting or processing multiple streams of quantum information simultaneously over one channel. It takes the classical idea of multiplexing using a resource efficiently, but turbocharges it with superposition and entanglement.
So it's not just dividing up the channel physically, but using the quantum nature of the information carriers.
Precisely. Superposition lets one qubit potentially hold aspects of multiple streams, encoded in those alpha and beta values. Entanglement helps coordinate these streams.
And this information is carried by photons. Spins.
Yeah, the physical qubits. Information gets encoded onto properties like a photon's polarization, which way its electric field wiggles or its phase, or the spin of an electron or nucleus. Then these qubits travel through quantum channels, maybe optical fibers, or superconducting circuits.
And the challenge is keeping them coherent, keeping that quantumness intact during the whole multiplexing process.
That's the million-dollar question.
Yeah.
Maintaining coherence is absolutely critical. Lose it, and you're back to classical information.
Okay, so Schneeppot then gets practical. How do we actually build systems that do this? He mentions photon spins, superconducting circuits.
Right. Photons, particles of light, are great for communication. They travel fast, relatively easily through optical fibers or even just air. You can encode quantum states onto their polarization, like horizontal or vertical, or their phase. Wavelength multiplexing is a key example here, sending different quantum signals on different colors of light down the same fiber.
Makes sense for communication. What about spins? That sounds more solid state.
It often is. You can use the spin of an electron trapped in a tiny semiconductor structure, a quantum dot, or even the spin of an atom's nucleus.
And the advantage there?
They tend to be much more stable. They hold their quantum state, their coherence, for longer than photons typically do. So they're really promising for building the processing units of quantum computers, where the qubits need to stick around while calculations happen.
Even if they're not great for sending info long distances.
Exactly, trade-offs. And the third big one Schneeppot mentions is superconducting systems.
Yeah, those seem to be everywhere in quantum computing news.
They are. You create qubits using tiny superconducting circuits with Josephson junctions. Think of them as artificial atoms in a way.
And their strengths.
They can be manipulated very quickly, which is good for computation speed, and they seem quite scalable. People are building chips with more and more of these qubits. Multiplexing here often involves using slightly different microwave frequencies to talk to different qubits on the same chip.
So Schneeppot sums it up. Photons for distance, spins for stability, superconducting for speed, and maybe scalability, but each with its own issues, especially decoherence.
Right. The best choice really depends on what you're trying to do. Send keys securely. Maybe photons. Build a big processor. Maybe superconducting circuits or spins.
Okay, let's get into the specific techniques Schneeppot outlines for achieving the multiplexing itself. He starts with polarization and time multiplexing for communication.
Yeah, polarization multiplexing with photons is straightforward conceptually. You send some qubits encoded in horizontal polarization, others in vertical, down the same fiber simultaneously. Different information streams on different polarizations.
And time multiplexing.
That's more like the classical idea. You chop the channel into tiny time slots. Qubit stream A goes in slot 1, stream B in slot 2, A in slot 3, and so on. Works well with fiber optics. But you need incredibly precise timing and synchronization at both ends. Nanosecond precision, or better.
Tricky.
Then Schneeppot talks about frequency multiplexing, especially for quantum computers.
Right. This is huge for superconducting qubits. Imagine several qubits sitting near each other in a small cavity on a chip. Each one is designed to respond, to resonate, at a slightly different microwave frequency.
So you can tune in to talk to just one qubit at a time, even though they're physically close.
Exactly. You send in a microwave pulse at qubit 1's frequency, and only qubit 1 really responds. Then you send a pulse at qubit 2's frequency. It's a key way to individually control qubits on a crowded chip.
Sounds powerful for scaling up.
Any downsides?
Oh, definitely. The qubits can still subtly influence each other, causing frequency shifts. You need constant calibration, error checks. It adds complexity.
Okay. Then Schneeppot covers wavelength and space multiplexing, thinking about larger quantum networks.
Wavelength division multiplexing, WDM, is basically the photon frequency multiplexing we mentioned. Different colors of light in one fiber. The cool thing, as Schneeppot points out, is that this is already used massively in classical telecom.
So we could potentially piggyback quantum signals onto existing fiber infrastructure.
That's the hope. You could have, say, quantum key distribution signals on one wavelength and your regular internet data on another in the same fiber. Very practical.
And space multiplexing, that sounds different.
It is. Instead of different colors or times, you use different shapes of the light beam, different spatial modes. Think of donut-shaped beams versus simple focus beam.
Whoa.
You can encode information in these different spatial patterns. It works best in special multimode fibers or free space links, offers another dimension to pack in more information.
So combining all these time, polarization, wavelength, space could really scale up quantum networks.
That's the goal. But managing all these different modes, keeping them stable, detecting them properly, more challenges.
Which brings us neatly to the elephant in the room Schneepat keeps returning to. Errors and decoherence.
Yeah, you can't talk about quantum tech without talking about decoherence.
Yes.
It's the constant battle. Those quantum states are just so fragile. Any interaction with the environment, heat, stray fields, even just the qubit bumping into its neighbors can make it lose its quantumness.
And multiplexing might even make it worse. More signals crammed together.
It can, yeah. More chances for interference or crosstalk. So error correction is absolutely non-negotiable.
Schneepat mentions things like stabilizer codes, steam, Shor codes, topological codes.
Right. These are clever ways to encode the information of one logical qubit across multiple physical qubits. It builds in redundancy. If one physical qubit gets corrupted by noise, you could detect the error by measuring the other qubits in a specific way and potentially fix it without ever learning the actual quantum information you're trying to protect.
Sounds incredibly complex.
It is. Topological codes, like the surface code, are particularly promising because they're more naturally resistant to certain types of errors. But we're still improving these codes and figuring out how to implement them efficiently. Better hardware shielding helps too, of course.
Okay, so assuming we can manage the errors.
Yeah.
What are the killer apps? Where does Schneepat see quantum multiplexing making a real impact?
Quantum communication is a big one, especially quantum key distribution, QKD.
For ultra-secure encryption keys.
Exactly. Multiplexing lets you send multiple keys at once over the same fiber, boosting the key generation rate. Or, like we said, run QKD on one wavelength and classical data on another. Makes it more practical, cheaper to deploy.
So higher bandwidth, lower cost, maybe even more security layers, but still fighting fiber loss and decoherence.
Always. You need error correction, maybe quantum repeaters for longer distances.
Yep.
It's ongoing work.
What about quantum computers? How does multiplexing help there?
Schneepat highlights how it enables parallelism. You can control multiple qubits simultaneously, using frequency multiplexing, for instance, to run different parts of a quantum algorithm at the same time.
Speeding things up even more than the basic quantum advantage.
Potentially, yeah. He mentions Grover's search algorithm as an example where multiplex control could offer further gains. It's key for scaling up processors to tackle meaningful problems in chemistry, materials, science, optimization.
But controlling hundreds or thousands of multiplexed qubits precisely, that sounds hard.
Immensely hard.
Yeah.
Control, complexity, and measurement accuracy are huge hurdles. But the payoff for efficient scaling is potentially enormous.
Schneepat also mentioned quantum sensing, using quantum effects to measure things super accurately. How does multiplexing fit in?
It lets you make multiple measurements in parallel or measure different aspects of a signal simultaneously. Imagine sensors monitoring magnetic fields at many locations at once with quantum precision. Or improving the bandwidth of detectors like LIGO for gravitational waves by monitoring different frequency bands. Or making atomic clocks even more stable by querying multiple atoms concurrently.
So higher data rates, more complex signal analysis, more sensitive detection.
Exactly. Though keeping those sensor qubits stable long enough to make the measurement is, again, the challenge.
And finally, the big picture. Scaling up quantum networks towards a quantum internet. Multiplexing seems essential there.
Absolutely essential, according to Schneepat. You simply can't build a large-scale network sending one qubit at a time. You need wavelength, space, time, multiplexing, probably combinations of them, to get the capacity needed.
He mentions things like the Quantum Internet Alliance, satellite links.
Yeah, these are early steps towards that vision, using satellites to bridge long distances where fibers aren't feasible. But synchronizing a global network, dealing with signal loss over thousands of kilometers. Huge challenges remain.
But the vision is powerful. Secure global communication, distributed quantum computing, networked sensors.
It really is. Multiplexing is the enabling technology that makes that grand vision seem even remotely achievable.
Okay, it's clear multiplexing is powerful, but Schneepat is also realistic about the roadblocks. Let's recap those key challenges. Loss and noise seem paramount.
They really are. In optical fibers, the signal just fades out exponentially with distance. That IZE alpha Z relationship, Schneepat quotes, you lose photons. And noise, thermal noise, environmental radiation, imperfections in the devices themselves, constantly tries to scramble the quantum state, causing decoherence.
And interference between the multiplex channels themselves.
That too. Signals bleeding into each other. Mitigation involves things like quantum repeaters to regenerate the signal, better fibers, better shielding, and of course, error correction.
Then there's the hardware itself. Schneepat notes limitations there.
Yeah, current quantum processors, whether superconducting or photonic or whatever, just don't have enough high-quality qubits yet. Coherence times are too short, error rates are too high, control isn't perfectly precise.
But improving rapidly.
Very rapidly. Better materials, better cooling systems, smarter hardware-software integration. There's huge progress being made.
Schneepat also flags algorithmic problems. It's not just about building the hardware, but controlling it smartly.
Exactly. How do you optimally assign qubits and channels in a complex, dynamic, multiplex network? How do you manage resources in real time? These are tough algorithmic optimization problems.
And controlling these large entangled systems, one small error could mess everything up.
It can cascade, yes. And simulating these systems on classical computers to develop the control algorithms is itself incredibly difficult, often impossible for large systems.
So how do we tackle that?
Schneepat suggests things like using machine learning to find better optimization strategies or improve error correction protocols. Hybrid classical quantum algorithms might also play a role.
So looking forward, what are the solutions and developments Schneepat sees on the horizon?
Well, definitely better hardware. Things like next-gen quantum repeaters, new qubit types, like topological qubits, which might be inherently more robust, or neutral atoms, which offer long coherence times.
And better error correction.
Continued advances there, yes. Making topological codes more practical, developing adaptive codes that adjust to the specific noise environment, and, importantly, combining different multiplexing techniques more effectively, maybe wavelength and polarization in space, all together.
Layering them up.
To really push the bandwidth. The ultimate vision driving all this, as Schneepat frames it, is that global quantum internet.
Okay, let's look further out. What are the future perspectives Schneepat discusses for the technology itself?
He expects continued gains in bandwidth and efficiency. Smarter combinations of multiplexing methods, better error correction, allowing more signals to be packed in reliably.
And making it smaller, more integrated.
Definitely. Scalability and miniaturization are key. Getting these multiplexing capabilities onto quantum processor chips directly, whether superconducting or photonic. And using AI for automated, real-time control and optimization.
New materials playing a role too.
Crucial. Finding materials that support more stable qubits, or photonic components with lower loss and noise. Things like topological materials for qubits, advances in integrated photonics.
And what about fitting this into the world we already have? Schneepat mentions integrating with classical networks, hybrid systems.
Yeah, that's a really important pragmatic angle. The idea isn't necessarily to rip out all existing fiber optics. Can we make quantum communication coexist with classical data?
Using shared channels like the wavelength multiplexing example.
Exactly. Send secure quantum keys on one color of light, your emails and video calls on others, all on the same fiber. It avoids the massive cost of building a completely separate quantum infrastructure initially.
Challenges there, though. Syncing everything up, cost.
Sure, integration isn't trivial, but it offers a pathway to bringing quantum advantages, especially for security, into the real world sooner rather than later. It could really start a new era of communication.
And the broader impact. Schneepat talks society, economy, research.
Potentially huge. Societally, think truly secure communication for everyone, for governments, critical infrastructure. A more connected world via that quantum internet.
Economically.
Massive potential for innovation. Finance, medicine, logistics could all be transformed by quantum computing, enabled partly by better scaling through multiplexing, plus a whole new industry building the quantum hardware, software services.
And for science itself.
It pushes the boundaries. It requires collaboration across physics, engineering, computer science, material science. It opens up new research questions and deepens our understanding of quantum mechanics itself.
Which leads to that ultimate vision Schneepat paints. The global quantum internet. What does that look like?
He describes a network connecting quantum processors and sensors worldwide. Distributed nodes, probably linked by both fiber and satellite for global reach.
And what could it do?
Unconditionally secure communication, globally. Distributed quantum computing tapping into powerful quantum computers remotely. Vast, highly sensitive sensor networks for science or environmental monitoring.
It's a long-term goal, obviously.
Very long-term, but it's the kind of grand vision that drives the field forward. Secure, efficient data exchange on a global scale, accelerating science, enabling new industries. It's transformative.
So wrapping this up, the deep dive into Yuri Schnepat's analysis really underscores that quantum multiplexing isn't just an incremental improvement, it's fundamental, built on those wild quantum rules of superposition and entanglement.
Absolutely. It's the key, as Schneepat argues, to unlocking so much potential in quantum communication, computing, sensing, and networks. It's how we take these amazing quantum properties and actually make them work together at scale.
But the challenges are real. Loss, noise, that pesky decoherence, getting the hardware to scale reliably.
Right. Huge engineering and scientific hurdles still exist. Advances in error correction, materials, control systems are all crucial.
Still, the outlook, as Schneepat presents it, is incredibly exciting. That prospect of a global quantum internet, secure communication, powerful distributed computing, it feels like we're building the foundations for the next big technological shift.
There are definitely big questions left. Conquering decoherence is probably the biggest, and we need to think about the societal implications too. But yeah, the potential is vast.
And quantum multiplexing, based on Yuri Schnepat's work, seems right at the heart of making it happen.
Couldn't agree more. It's a crucial piece of the puzzle for this next revolution.
Thank you for joining us for this quantum deep dive.